Hello guys, I hope you can hear me, and apologies for being late by 5 minutes. Right, I was just preparing something for you guys, just to illustrate your assignment maybe in a much simpler way. So first of all, both of you, Joel and Ruben, both of you able to hear me loud and clear?
Yes, sir.
Okay, that's good. Okay, it's just Sandeep. Okay, I'll keep reminding you. Okay, so Joel, how about you, Ruben? Maybe a yes and a no from you would help. Anyways, Ruben appears to be very quiet. So all of us are here. Okay, so see, so this is what is happening, right? Okay, you are given an electric motor which transmits a power of. Are you? By the way, are you able to see my screen and all the drawings which I have on it?
Yes, sir.
Okay. So there's a motor here on the left, and that generates 75 kilowatts and so of power. As a result, you see this input shaft, it will start to rotate, and it rotates at a constant speed of 25 revolutions per second. So it has a diameter of 48 mm, right? Okay, and this part here in between, the flange coupling, that is actually what you are going to design. Okay, so coupling means two, okay, and a left and a right, one for the input shaft, one for the output shaft, and both will be connected using bolts. Okay, you could also weld it in place, but in this case, you're given the option of using bolts, and the dimensions, I mean, all the information regarding all the technical specifications for the bolts are provided to you, right? So when we say design, we mean that given all the parameters, the input parameters, you should design a flange coupling which does not, or which does the task, or which performs the task of transferring that power generated from the motor to the gearbox via the output shaft. Okay, again, that output shaft also has a same diameter of 48 millimeters, right? So what we did on Wednesday, the last thing I asked you to do was to calculate the torque, right? So the torque generated, that is the only load which will be acting on the entire system. When I mean system, I mean the shaft, and the same load will be acting on the flange coupling, and the same will be on the output shaft, and okay, so from there onwards as well, right? So I hope that clarifies everything, if in case it was a bit confusing on Wednesday. So for the torque calculation, I did say you have to create a proper documentation in terms that you will say that, I don't know, you could say that this is just I think the first and the last time I'll be just giving you a sample calculation, whereas the rest are pretty similar. So to determine the torque acting on the input shaft, the equation used was, okay, then here you can just set the equation, I suppose. Oh, it's not allowing me to insert equation. Okay, you can, to find the torque, that's pretty much the equation you will use, right? Yeah, so you can just put that in the center, and then please do add all this information where P is the power in, what would you use for power in this case? It would be watts. Okay, try to use the standard units, okay, so it makes your work easier. So watts, and what else? 2 pi n is the rotational feet, and in our case it is revolutions per minute, RPM, and what else? And T is the torque given by Newton. Torque is calculated in Newton meter, right? Force times distance, pretty much. Okay. And after this, you can center the thing. Right. So you can input your numbers in your equation. Right. In this case, it would be power is how much?
75.
75 kilowatts. So if you can read, so kilo would be 75,000. Oops. And T is the subject of the formula. So you can convert what is it, 25 revolutions per second into revolutions per minute, which would be 25. Okay, so that will be 25 by 60. Okay, please do correct me if I'm wrong. Right, the 25 by 60 is to convert 25 revolutions per second into 25 revolutions per minute. Okay, and then divided by 60. So as a result, you will get the value for T as so tiny. And pretty much underline this, so torque will be equal to whatever answer you get, right? Okay, so that will be a torque. And after this, you'll, okay, it is a good habit, okay, to write in words. The input shaft torque is so and so Newton meter, right? Okay, so pretty straightforward calculations, I would say, at this stage. Now, if we go back to our slide here, yeah, so that is pretty much it in the beginning. So we are trying to find the torque at this stage, and which is acting on the input shaft. Right. Okay. What's the next bit of analysis? So the next one is the key analysis, right? Okay. So just a little bit of explanation, right? For the key analysis, what we are trying to find is, okay, so there you could see the key. And let's see if we have any other, some other pictures to show the key. How does it look like? Someone must be here, must be here. Anyways, so what we are trying to do here is find the length of the key, which is that, okay? The length of the key. That's the width of the key, and that's the thickness of the key, okay? How thick the key is. Right. So when you guys calculated the torque which is acting on the shaft, we said the torque is equal to F by R, right? Okay. So my question to you guys would be, just by looking at this figure, in here you have pretty much three types of forces, which I think either compressive force or tensile force or shear force. Okay, now try to imagine this scenario. You have a shaft, and on top of the shaft you have a key, and surrounding the key is a, yeah, there you go, surrounding the key you have a hub. So what kind of a force will be acting on the key? Okay, will it be compressive force? Okay, the answer is pretty much in this figure. Will it be compressive force, tensile force, or shear force? So remember, it's now when you, as soon as you turn on the power, the shaft which is connected to the motor, it starts to rotate, right? Starts to rotate. The key is fixed onto it, okay, or fixed in place. And now the key also rotates. Now the key is a sort of like a locking mechanism for the hub. Okay, the hub is given here in orange, right? So now the key locks in place the hub, then the hub rotates as well. So what kind of a force would be acting on the key while it is in motion? Any ideas?
Yield stress.
Yield stress? No, no. Either the just the three. You have three options: either compressive force, tensile force, or shear force. Compressive force means you are trying to compress from both sides. Okay. Shear tensile force would be you trying to pull from both sides, and shear force is a force which breaks things. Okay. In other words, how would I put it? If you're taking a loaf of bread and slicing it with a knife, technically you would say you are shearing that loaf of bread. Okay, so you have three options. Which one would do you think? The answer is given in the diagram in front of you. Think about it. Let's see if I'm able to draw on this. Ruben, what do you think?
Shear force.
Shear force, exactly. Right. So what will happen now, if you notice in this figure, so half of the thickness of the key is inside the shaft, and half of the thickness of the key is outside of the shaft. Right. Okay. And if you see the diagram, yeah, if you see this diagram of the flange, uh, this part here, that's where the key will slot in place. Okay, this has a keyhole, the hub has a keyhole, right? Okay, so half of the key which is protruding outside of the shaft will be inserted here, right? So where was I? Okay, so it will be experiencing shear force, right? Okay, so that's the reason. So coming to the next slide. Okay, so when it comes to the next part of it is Control C. When we are coming down to the key analysis, determining the key length, right? Okay, so now why do you need the dimensions of the key? So that you are able to draw it out in AutoCAD, right? So using the equation, so now you'll use the equation. You know the torque value is equal to the shear force multiplied by R. Okay, in this case, R is the shaft radius. Why do you think it is the shaft radius? Look at this diagram here, right? So shift F5. So as I mentioned, yeah, right. So from the center, I hope I can get it in place. From the center, to that point, right? That's pretty much the radius of the shaft. And why because that is the point where that shear force, which Joel mentioned, that is, I mean, sorry, which Ruben mentioned, that is the point where that shear force will be acting. So as a result, now you're able to see that the top half of the key is sliding off. In other words, it's not, it's in, you could more specifically say that it is shearing off, right? Okay, so half of it is inside, half of it is outside. So that's basically half, I mean, that's basically the radius of the shaft, right? Let's get this. Start. Okay, so where am I? Right, so now you will make the shear force the subject of the formula, right? So torque is equal to, I mean, sorry, shear force is equal to torque over R, okay? And in that case, you will be able to find what the shear force acting on the key is, right? Okay. Are you guys both okay with this at the moment before I proceed further?
Yes.
All right. Okay, I'll probably maybe note it down here. Just put this determine the key length. So what you're required to do is let's say from the key size data given the assignment brief for a shaft diameter of 48 mm, 48 mm, right? The key dimensions are, right, the width of the key is the thickness. Okay, now just, so we are after the length of the key. In the meantime, the data on the width and the thickness of the key is provided to you, right? Okay, so if you go to your assignment brief, for the key, so we did say that the key is made out of steel, right? Okay, and so that information is known to us. And so now if you go to page. Okay, so if you go to the last page, which is page number 4, so the table right at the bottom, it gives you a standard key section dimension with its tolerance, right? Okay, so in other words, what this table is saying, so if there's a shaft size of this particular dimension, its corresponding key length, I mean key width and thickness is supposed to be so and so, right? So in our case, the shaft size given is 48 mm. So you find where in which range 48 mm falls in, and then correspondingly you should be able to determine the width of the key as well as the thickness of the key in millimeters, right? So I've pretty much pointed this out to you. Okay, so in our case, the width of the key is 14 mm and the thickness of the key is 9 mm, right? So the only dimension left for us is to determine the length of the key, right? So 14 and 9, that's 14 mm and 9 mm. Right on. So now, so our assumption is that the key will fail as a result of shear stress acting tangential. Okay, once again, this is I'm writing all these notes down so that it is easier for you guys to follow. In your case, in your report, please do write in your own words. Okay, right? It'll look pretty much original. So tangential to the shaft. Okay, and then you can put down the formula here, which is shear force is equal to, right? So shear force will be equal to over R, which is R in this case would be the radius of the shaft. And so shear force and R the radius of the shaft. Right. Once again, please do put down the nomenclature. It is as in you could try to where Fs is the shear force and T is the torque and R is the radius of the shaft, right? So and so. And after that, you do your calculations. This is where your calculations should come in. Okay, I'll just maybe put a hashtag and just right here do calculations for shear force, right? Right. Okay. Okay, and so similarly as you did for the torque, do your calculations for the shear force. Right. Okay. Now going back to the figure once more. Okay. So now let's see. You have so you have the length of the key, you have the width of the key, and you have the thickness of the key. Right. So which area is experiencing shear force in this case? Okay, or to put it more simply, what do you know about, or how do you find stress? Or how do you find stress? What is the calculations you have learned in from previous years about how to find stress mathematically? If you know the force, what would you say? Anyone? You can even look up this particular slide as well. It shows you how to find the stress. Stress is equal to force over area, right? Okay. So we all agreed that the key will experience shear stress. Okay. So you could say the shear area of the key the shear stress acting on the key. I hope you guys are still here. So the shear stress acting on the key is given by the equation. Okay, so you can note down this equation. Control C. Let's put it in the center here. Right. This symbol here on the left is for shear stress, right? It is known as tau, right? So the shear stress is equal to force over area. Okay, so stress is equal to, generally speaking, stress is equal to force over area. So you could say, now you know the shear force. I'll just put down Fs. So for simplicity's sake, so the shear force, stress is equal to shear force over the area, okay, of the key which is causing that particular shear, right? So then you could say the shear area of the key is, okay, now I would want suggestions from you guys. How would we find this area? Okay. That's what we are after. Okay, so the area. Now going back to this diagram once more. So you have three dimensions for the key: the length of the key, the width of the key, as well as the thickness of the key. Now, again, it's pretty much obvious from this diagram which area is experiencing the shear stress, okay? And that area, part of that area is shown in red, right? So which two will it be? Will it be the length multiplied by the width, or will it be the length multiplied by the thickness, or the width multiplied by the thickness? Any suggestions? The three of you?
Samdeep, would it be length times the width? No.
The length times the width. Let's see. That's the length multiplied by the width. Yes, yes, it will be the length. So that's why it's indicated in red, right? So in other words, the top half, once the key fails, or if the key fails, the top half of the key will basically slide off, okay, or shear off. So that all of that area which will experience that shear stress is pretty much the length of the key and the width of the key, right? The answer is here, given here. What is it? Okay. Oh no. Yeah. So the key shear area is the length of the key multiplied by the width of the key. Okay, 10 more minutes we have left, right? Okay. So yes, you guys got it. So area will be the length of the key, L, length of the key multiplied by the width of the key. Okay. Becomes simple now. So what was our task? Was to determine the length of the key. There you go. By the way, yes, given this formula, after you write down this formula, you have to find what? What will be the variable here? Tau, force, or the area for this formula, for this one. You know the shear force? Yes, from your previous calculations. I should also note this down here, in case you forget. Hashtag do calculations for area. Okay, so how would you find this value, the shear stress value acting on the key? Are we given that, or have you guys found that out previously? We said that the key is made out of steel, yes. Okay, and the shear working stress acting on the steel is 28 Newton per millimeter squared or 28 meganewton per meter squared, right? So that value here, 28, will be here, the tau value, right? So you know this, you know the shear force, make area the subject of the formula and find out that area. So in order to find the length of the key is, whatever the length of the key is, so you will need to do calculations once more. Calculations for the length of the key, right? Okay, so from your previous calculations, you know the area of the key, length of the key is the subject of the formula now. The width of the key you have been made aware and we have noted it down, okay, which is 14 mm. So make the length of the key the subject and do calculations for it, okay? And if you are stuck somewhere, just refer to this slideshow, your PowerPoint presentation. So once you rearrange, you will be able to find the length of the key. And you're done with the key analysis then.
Sandeep,
Yes.
sorry to disturb, but I just want to ask that do you have to convert those mm dimensions into meters? No,
Mm dimensions into meters.
the width and the thickness.
It will depend, right? So let's say in my case, what is mine? So for my tau value, for my stress value, I am using 28 Newton per millimeter squared, right? So once I start doing my calculation, this is for my case only, right? So the shear force value I will get, it will be in newtons, right? And the stress value I will input here will be in Newton per millimeter squared, and F will already be in newtons. So the after doing my calculations, the area I will find, the area will be in millimeter squared, right? Then I will input it in millimeters. So directly the answer I will get, the length of the key will be in millimeters, okay? Right. So that's why I said from the beginning, be consistent with the units. Let's say, for example, if you use 28 Newton per meter squared, okay? So once you start doing your calculations, for the width of the key, you will have to input meters, right? Is that clear? Who asked the question? Joel, was it you?
Yes, thank you, sir.
But are you sure now? Or was it a bit confusing the way I explained it?
No, I'm sure. That's
Right.
fine.
Okay, no, it's fine, right? Okay, so after the length of the key, then you will move on to the, what else is there? Next part is the hub analysis. Okay, now I am pretty much sure that things should be quite simple for you, right? We'll go over the hub analysis part next week. Okay, so for the hub analysis, the hub or the boss means the same thing. What you are trying to find is what is the thickness of this hub. Okay, so it says determine the boss outside diameter. By the way, just by looking at this figure, what is the boss inside diameter? Very quickly, before we round up.
48 millimeters.
It is, what did you say?
48.
48, yes, exactly. The hub or the boss inside diameter is equal to the diameter of the shaft, right? So once you start doing your calculations, all you need to do is find the outside diameter of the hub or the boss. Okay, once again, the formula is the same. Now, for the key analysis, the first thing you determine what type of stress was it under. This time around, you have to determine for the boss or the hub, what type of stress will it experience. Okay, so FT is given. So I think it's pretty much tensile stress, right? The procedure for calculations are pretty much the same. Right, so is it okay if I end the things early here today?
Yes.
Yes, okay, so Joel is fine with it. How about you two, Jim and Ruben? Maybe you just can give me a feedback if you are fine with today's session.
Fine, thank you.
Ruben, okay with everything?
Good.
Okay, great.
Sandeep,
Yes, yes.
I would just like to ask, will we have this session next week as well?
Next week.
Yeah.
Yes, yes, yes. Are you okay with you guys are okay with Wednesday and Friday? I mean,
Yeah, okay.
yeah, I'll just pretty much be having it at. I'll try to have it at the same time on Wednesday as we had it this week, and same time on Friday. So by next week, Wednesday and Friday, we should be able to round up all the calculations. The only thing left for you guys to do on your own would be to put your drawings on AutoCAD, since you'll be aware of all the dimensions and features. So I hope that's fine. That's the reason I'm going really slow with this, because we still have time.
Okay. And one more thing, Sandeep.
Yeah.
We are finding this, this problem with AutoCAD by all the lines go missing when you do the solve command.
Oh.
We're not getting it, the 3D drawings. So if
Solve Prof, right? That's solid profiling, isn't it?
Yeah, when we hide the lines on the layout page, and when we go back to the model page, and when we orbit the 3D drawing,
yeah,
like from the front, the lines go missing. It's perfect, but when we turn it to see the lines at the back, they are not there, like that, half missing.
Okay.
So is it the way it's supposed to be, or are we doing something wrong? Because I emailed Crystal.
So okay. See, it is correct. When you're doing solve prof, so it will create profile. There will be a visible profile. There will be a hidden profile. So if you turn off the hidden profile and only the visible profile is showing, so if you omit your drawing, you're saying the lines at the back are missing, isn't it?
Yes.
Yes. So it is supposed to be like that.
Okay.
Right, because what happens now, your drawing has been like not torn apart, but it has been separated into two profiles. Just like if you draw a simple cube, the lines which are at the back, they become the hidden profile. If you draw a cube in 3D, that is, and the lines which are visible from the, let's say, the front, okay, or the isometric view, they become a solid profile. So if you turn off the hidden profile, or even if you do the solve prof command, after that, the layers of hidden and solid profiles, they will separate.
Okay, that was only the confusing part we were facing, but thanks.
No, it's supposed to be like that.
Okay.
Maybe what I'll do is after, maybe, so you have a lab regarding the solve prof which is due this week?
Yes, we are doing a 3D drawing, Lab 7. It is also a 3D drawing, yeah.
Yeah, because it's the same thing is you have to submit, isn't it? So
yeah.
After solve prof. Yeah, so it is that way.
Okay.
Okay.
Thank you so much.
Set anything else? No. Yes. Okay, so that's all for today, right? And I'll probably by